Now, there are different modes of transducer operation used in medical ultrasound. The first mode is the continuous mode or the continuous wave transducer. With this, there is one crystal that vibrates and a separate crystal element that listens for the returning echoes. So there are separate elements for the transmission and the reception of ultrasound. For pulse transducers, the same element crystal is the one used for sending and receiving the sound energy. So what will happen is that the crystals will vibrate for a certain period of time, and then it will stop and listen for the echoes. And when the echoes arrive, the echoes make it vibrate, and then the vibration will create electrical energy that will be sent back to the CPU. So the pulse transducers will pulse and then listen, will transmit and then listen. And so it is up to us to apply the settings of the pulse on how long a period of time that they will pulse and how long a period of time that they will listen for the echoes. And again, in the lecture on knobology, you will be told how this is very important in adjusting now for the improvement of the detection of the ultrasound. So this is a figure example of a continuous wave mode where there are two different piezoelectric elements. One element will continuously vibrate and send forth the ultrasound signals, and this will be echoed back and picked up by a second transducer or a second crystal, which then transmits or converts the mechanical energy into electrical energy, and electrical energy is brought into the receiver, and this receiver is then interpreted by the central processing unit, and then it's again amplified and brought out to a speaker, so you are able to hear the sound. If it is not through a speaker, it is brought out through a display monitor where sound is converted into light energy. Now, the pulse wave system, you only have one crystal which vibrates for a certain period of time, then it waits for the echo. And it is this system that sends forth the signal and receives the signal and sends it back to the central processing unit, where it can be shown as a monitor display, or it can be demonstrated and amplified into a loudspeaker. So we've been talking about echoes being picked up by the transducer, and this is now an important concept, the concept of pulsed echo principle. When an electrical pulse strikes the piezoelectric crystals and produces a wave that propagates through the tissue, then the echo is picked up by the crystal, and then it generates an electrical signal that is sent to the central processing unit. The returning waves are converted into electrical impulses that form the ultrasound image. So again, the beam is the directed acoustic field produced by a transducer, and the transducer is the device that is capable of converting energy from one form to another. We have to look now at the beam anatomy, because the beam anatomy and the beam behavior can affect how the transmission of sound and how this sound can be processed further. Now, because of the pulse echo principle, we want to capture as much as possible, as many echoes as we can, because if we do not capture too many echoes, then the energy is lost or the sound is lost through scatter, and you will have a very weak amplitude. So you want to orient your ultrasound probe into, as much as possible, a perpendicular location to your organ of interest. So if this is the surface of your organ of interest, you want to position your probe such that the beam is nearly perpendicular to the surface of the organ of interest, so that you will have strong echoes coming back. Because if they are not parallel, or if they are not perpendicular to the direction of the waveform transmitted and reflected, then you will have a lot of scatter, and you will only be able to capture very weak signals. And there is going to be a great degree of attenuation in your reception of the reflections and echoes. Looking at the beam and the beam anatomy, we know that it is a longitudinal beam, but the beam has a focal point. The beam has a focal point. And there are two areas or two regions in the beam. The region before the focal point and the region after the focal point. This is very important to know, because the organ of interest, wherever it is in the beam anatomy, it may result in very poor resolution. So resolution is just defined as the ability of the system to discriminate or to differentiate adjacent points or adjacent structures. So if you have good resolution, then that means you're able to resolve two different points or two different structures. Because if you cannot resolve them and the two structures are seen as one, then there is very poor resolution, and then you get a very blurry image. Beam anatomy has a lot to do with resolution. As much as possible, you would like to have the organ of interest at the focal point of the beam, and you will have to adjust your machine to put the focal point to your organ of interest. However, if your organ of interest is at the region that is closer to the transducer, or what is called the near zone, this near zone can also afford good resolution. So there are two kinds of resolution. Axial resolution is the ability to distinguish between structures along the path of the ultrasound beam. So if this is your focal point over here, and these are your organs or target organs of interest, at the focal point, you will see that the target structure is well resolved. And at the focal point, these two structures can be seen as two different structures, so they are well resolved. But in the far zone, you have two structures here, but it will come out in the ultrasound as only one structure. Then these two structures are not finely resolved, and you only see one structure, which is a very bad resolution. So you will have to position the structure into your focal point or closer to your focal point in your near zone in order to have a good resolution axially. The same thing happens with lateral resolution. Lateral resolution is the ability to distinguish between reflecting surfaces perpendicular to the path of the ultrasound beam. So in this example here, you have 3 points, and there is, because it is in the far zone, the resolution is so poor that point 1 and point 2 is not completely resolved and it can be seen only as one structure. Now we can resolve point 2 and point 3 as different structures, but point 1 and point 2 are not resolved, and so there's poor resolution at this level. So this is where we now understand why we need to put structures of interest or organs of interest at the focal zone, or at least closer to the near zone. Or this near zone, or what we call the Fresnel zone, is the area between the transducer and the focal zone. The focal zone is where the diameter of the sound beam is at a minimum, and that is where there is a very, very clear resolution. And the far zone is the area extending beyond the focus. This far zone, or the Fraunhofer zone, will offer you only very, very low resolution. See, in here in the Fresnel zone or the near zone, you can still have very good resolution, but after the focal point, you will not be able to resolve the two dots or the three dots, and you will just see them as singularities. Now, what can affect the focal point? And so what can we do to improve the focal point of the ultrasound beam? The length of the Fresnel zone or the length of the near zone can be affected by the size of the transducer. And it can also be affected by the frequency of the vibration. If you have a lower frequency, then you will have only a shorter near zone. Okay? If you have a higher frequency, then you will have a longer near zone. So here, with the same size of the transducer being kept constant, but the frequency is increased from 1 megahertz to 3 megahertz, you will see that the near zone is becoming more elongated. And so you will be able to see a little more good resolution with higher frequencies as long as it is kept in the near zone. So the second variable is the size of the transducer. The near zone is elongated if the transducer is increased in size. So here in this diagram, with a frequency being kept constant at 1 megahertz, with the size of the transducer becoming bigger and bigger, you will see that the length of the near zone is becoming longer and longer. So that with the size of the transducer, you're going to have a longer near zone, which means you will have a greater distance of a higher resolution. So talking about frequencies, again, I bring this back. Higher frequencies will have a high resolution, but the caveat is that it will also have a high attenuation and therefore low penetration. Lower frequencies will have low resolution, but there is low attenuation, so it can travel further. It can travel longer distances, and thus it has a higher penetration into our bodies. And so when you choose a probe, when you're going to buy your ultrasound, you will need to know what usual target organs you're going to use, or you're going to detect, because that is the frequency of the probe or the transducer that you will need. If you're only going to look at superficial structures, like structures at the skin, subcutaneous area, or even up to the muscular layer of the extremities, soft tissues of the neck and of the breast, then you will need a higher frequency ultrasound probe. But if you are going to look at body cavities or body depths, like the pelvis, the abdomen, the heart, which is situated kind of deep inside the thorax, then you will need ultrasound frequencies of the lower frequency kind, because they will have low attenuation and high penetration. But remember, they will also have low resolution. So applications is that the transducer frequency you will choose to buy or you will choose to procure, if you're going to use it for abdominal, trauma, cardiac, obstetrics, you will want to get transducer frequencies from the 2.5 to 5 megahertz range. If you're going to use it for pediatrics, prostate, rectal, transvaginal, intraoperative ultrasound, you usually use a higher transducer frequency of 4 to 8 megahertz. Now, if you're going to look at small parts, the breast, testicular parts, vascular, muscular, endorectal, you want to look at the different layers of the anorectal region, then you need a higher frequency because it is very shallow. You don't need one that penetrates very, very deep, and it affords a very, very good resolution at that frequency. So here is just a diagram of the pulse bandwidth and resolution. And resolution is affected by the pulse bandwidth. We talked about the pulse echo principle, and we talked about pulse wave versus continuous wave. So the pulse wave will have an effect on your resolution. So if you have a longer pulse, that means you will have a narrow frequency, then you might be able to get a greater resolution with a longer pulse. But with a short pulse, you have a broad signal there, and you have only one frequency. Then again, you have a low frequency. Then you have a very low resolution in that situation. So you will have to learn in your knobology how to adjust your pulse frequencies. The transducers in the older days are designed with only one frequency per transducer, and that is why you have to specify to your ultrasound distributor what kind of transducer and what kind of frequency that you would like to use for your particular use. Currently, though, transducers are designed with a high bandwidth and can be operated at different frequencies. The user is able to control the trade-off between penetration and resolution for the same transducer. So now all you need to do is tell your distributor, I want these frequencies and I want them included in one transducer. So now there are now settings in the ultrasound machine where you can change the frequency. Before, you used to buy a different probe for a different frequency. Now there is such a concept as multi-frequency imaging where you can change the frequency settings of one transducer. So finally, we come now to the final component, which is the conversion of the electrical energy into light energy so that we can now see what the ultrasound echoes have been picked up.